Hello, welcome to this video mini lesson introduction to the chi-square test of independence. Okay, so before we go into our example regarding fifth graders' choice book genres, let me just point out a couple of things. First of all, the test of independence is used when you have more than one variable. So in the example that we used previously for goodness of fit, we were looking at fifth graders' choice book genres, and we were doing it for all the students put together. This time we're going to break it into males and females. So we'll actually have two variables. One will be the genre of their book selection, and the second will be gender, and we'll put males and females in two different rows here. So that's known as a two-way chi-square. Now, there are some assumptions for two-way chi-squares. First of all, that the categories are independent of one another. So that, for example, we're not talking about siblings here as opposed to genre or something. And that we do not have any expected frequencies of less than 5 in any cell. Now, if you do have a cell with an expected frequency that's less than 5, if you have a 2x2 table, so that would be like two genres in two genders, male and female, then you could do what's called the Yates correction factor. However, that's only for a 2x2 table. So other options would be to collapse collapse categories. In our situation, instead of having 7 different genres, we might just have realistic, fiction, science fiction, nonfiction, and other. So just reduce it, say, to 4 categories, in which case an expected frequency of less than 5 may not occur in any of our cells. And also you can add cases. So instead of just doing this for one class of 70 students, or one team of 70, maybe I do it for the entire grade of 5th graders to increase my case size, my sample size there. All right, so let's go ahead and go back to our example. So we have our genres here, and we're going to add our second variable, which is going to be gender. So I am increasing the size of my contingency table here. And so we'll say that this is males and this is females, okay? And then what we also do, once we increase to a two-way contingency table here, is we'll then add a column, or excuse me, a row for totals as well. So here we have the total, the marginal total for our columns. Marginal total is just sort of like a subtotal. So this will be the total for each of my columns. And then I'll have my total over here for my rows. So that's going to be my marginal total for rows. And then down here in this cell, I'm going to have what's called my grand total, okay? Now, when I was doing this before, I just had an n size of 70. So we're going to keep this data that we already had. Now we're just going to say that it's for males. So the n size for males is 70 here. But we're actually going to add 80 females. So now our total n size is going to be 150. And we're going to have 80 females here. And let's just say that for the sake of our purposes here, that we have 2 females who selected humor, 5 nonfiction, 10 science fiction, 5 sports fiction, 20 action, 35 realistic fiction, and 3 other, okay? So then I could get my marginal totals by column here just by adding these all up. And then I've got my marginal totals for my rows, and so my grand total is going to be 150 cases here. All right, so now what we would be doing with our test of independence is we're trying to determine whether there are statistically significant differences in our males and females as far as how they select the genre for their independent, or not how they, but what genre they select for their independent book choice, okay? So, let's see here. Interestingly, the formula that you use for the test of independence is the exact same one that you use for goodness of fit. So whether you're doing a one-way chi-square or a two-way chi-square, it's the same formula here. Now, a couple of things will differ. For example, with a two-way chi-square, the way that you would calculate your expected frequencies, and this is if you have equal probability, you take your marginal total for your rows, multiply that by your marginal total for your columns, and then divide that by your grand total. And the reason that you're doing it this way is because these have to be weighted expected frequencies based on the number of cases you have in your different categories for your independent variable. So in this case, I have 70 males and 80 females. So that's an uneven case size across my independent variable. So this will allow you to weight your different case sizes by category so that you're still getting an equal probability for each of the categories based on the weight, based on the total number of cases in that category of independent for your independent variable. All right, and then just like with the goodness of fit, you have to use your degrees of freedom in order to look up your chi-square in a lookup table to find out the exclusion value. So your degrees of freedom, oops, that's for one way, excuse me. For two-way chi-square, where's degrees of freedom for two-way chi-square? Oh, where did it run off to? It's right in front of my face. For two-way chi-square, you have your degrees of freedom is your number of rows minus 1 multiplied by your number of categories minus 1. And again, you use that lookup table for the exclusion value. And if your actual chi-square exceeds your exclusion value, then you have a statistically significant finding. So in other words, your data supports your alternate hypothesis instead of your null hypothesis. So this is a bit of oversimplification of chi-square, but it does give you a bit of an introduction to the test of independence. Now, in the example that we looked at in the very first video mini lesson, the study from Ingersoll and Orr, we had two examples of two-way chi-square. Here we have dropout risk examined by gender. Here we have dropout risk examined by whether each participant had run away from home ever. And if you went ahead and you applied your chi-square formula and then used your degrees of freedom and the lookup table to find the appropriate exclusion value and compared your chi-square to the exclusion value, you would find that there is not a statistically significant difference in dropout risk by gender, at least there wasn't back then, but there is a statistically significant difference in dropout risk by whether or not a participant had ever run away. And as you can see here, running away actually increases your dropout risk by about 8-fold. So here's what's interesting. When you are doing a chi-square interpretation, then what you want to do is have in parentheses the percent that each of these actual frequencies represents. So, for example, we would take the total here, our marginal total for the row of, what would that be? 270. So that would be my marginal total for row for this particular row. And then I would find out what percent 53 of 270 is. And that is, let me grab out my handy dandy calculator here. So 53 divided by 270. So I have about 19.6% of my marginal total for my row is students who had at some point run away, who also had a high risk for dropout. So that's 19.6% of my total. Now, interestingly, those who had never run away, so I have to first of all find my marginal total here. And now I can find my percent. So if you've never run away, then your only about 2.9% of the time do you fall into the high dropout risk category, which is obviously a huge difference between students who had ever run away and those who had never run away. So it's about close to about sevenfold increase there. So my point here is that when you're trying to interpret contingency tables that are statistically significantly different, you want to offer your percents in parentheses so that you can talk about the difference in percent likelihood that a case would fall into one category versus another. As always, let me know if you have any questions, and thank you for your attention. Bye.